So hello everyone, this is lecture 2 for the thermal physics. In the last lecture, we discussed the KTG, that is kinetic theory of gases. We discussed this how we can find the pressure inside a box due to a n number of particles, and if we know the density, we assume some assumptions, then we calculated the pressure. That was 1 by 3 and mv square. So check out the last lecture. Only after that you can understand the second one. Okay. So just go with the sequence. Okay. So today we will study that how heat capacities of gases affected in the classical approach. Means how KTG influence the heat capacities and all these properties. Okay. So let's see, from KTG we learned that energy of a single particle is 3 by 2 kT. Means it's independent of the nature of the gas. It will be just 3 by 2 kT, which is where K is Boltzmann constant. Okay. So it is nothing but per molecule. One molecule will have this amount of energy, and per mole, if we calculate for the 1 mole of gases, the average energy will be, this is Avogadro number, that is E, that will give you 3 by 2 NaKb, that will give you R, that is gas constant, 3 by 2 RT. So this is the thermal energy for the 1 mole of gas of any nature. Okay. Means it should be monoatomic actually. So what is heat capacity? What is heat capacity? So generally the heat capacity is nothing but the amount of heat required to raise the temperature of a system or a particle by 1 Kelvin. So that we call heat capacity. Then there comes the terms specific heat capacity, molar heat capacity. So what is specific heat capacity? That is the heat required to increase the temperature of a system by 1 Kelvin and per unit mass. Okay. So per unit mass, the amount of heat required to raise the temperature by 1 Kelvin will be called specific heat of that gas. Okay. And that molar heat capacity is nothing but the heat required to raise temperature by 1 Kelvin for 1 mole of gas. Okay. So Cv is nothing but du by dt. Why it's du by dt? Because it's dq by dt. But from the thermal, we will study the thermodynamics, the first law, which says q equal to u plus w, where w is p del v, and delta v equal to 0 because volume is constant. So here q is equal to u. So that's why we taken here du by dt, and from this we can calculate that Cv will be 3 by 2 r. Okay. And we know from the Mayer's law, that is Cp minus Cv equal to R. So Cp will be Cv plus R, that will give you 5 by 2 R. So this is nothing but it's a constant for all the monoatomic gases. Okay. It's independent of the nature of the gas. And here we will calculate one more thing, that is ratio for Cp by Cv. We call it adiabatic index. So for any gas, this will be 5 by 3, 1.67. So this is the maximum value of adiabatic index that is possible. Okay. So according to KTG, the molar heat capacities and their ratios are independent of temperature and same for all gases. So this should be same for all gases. That's what we take the conclusion. But now we will study that how things gonna change. Means according to this classical approach, this should be this only. This should be same for everything or every gas. Okay. But then we have some practical results. These predictions that are based on KTG agree well with the experimental data shown on table 1. So this is the table, the heat capacities for a few common gases at room temperature. So let's observe, these are the actual quantities or the experimental values we measured. So we'll see that how theory is validating these or not. So these are helium, argon, hydrogen, oxygen, nitrogen, carbon dioxide, and the ammonia. So for helium it came to be 2.98, and for argon it is also same. For hydrogen it's increased, oxygen it is approximately 5.4, for nitrogen it is approximately 5. Again these all three values are approximately 5, and this is 6.8, this is 6.65. So these values are increasing. Means what is atomicity? Atomicity is how many number of atoms you are having in a molecule, that is called the atomicity. So here are 1 1 only monoatomic, so we have the minimum. and as the atomicity is increasing, we see that heat capacity is increasing. Heat capacity is increasing, and if we see the gamma, the adiabatic index, that is decreasing with the atomicity. So downward atomicity is increasing and gamma is decreasing. Okay, so when we see these observations, then we dig deeper inside these formulations. Means this should be, there should be some more inside. Okay, well, it can't be just fixed for all gases. Means we are seeing that for the different number of atoms in a molecule, means atomicity is, if atomicity is changed, then we are seeing some difference in the specific heat and the adiabatic index. So how we can explain these things? Then we move on and dig deeper. So what are the conclusions? For diatomic and polyatomic gases, discrepancies can be seen in the table. So CP/CV gamma experimentally decreasing with increase of atomicity of a gases. These are the conclusions we take from the table. To further gain an insight, the concept of degree of freedom is introduced. Now to digging further, so the concept of degree of freedom is introduced. Means there is something which is changing the heat capacity, increasing, decreasing and all. So let's see. If we take a monoatomic gas, then it is just moving in the 3D space. Then we know that only the three translational motion are possible, that is in the x, y and z directions. So how many degree of freedom will be? Only three translational, means or either in x, either in y and z. So any point inside this space you can draw, then that movement will be in three directions only. So that's why a single monoatomic gas will have 3 degree of freedoms. Okay, so let's discuss the diatomic case. If there are two atoms in a molecule, then let's say we put it on this axis, and now we can see the movement of this is a system. Now this whole system is, how many degree of freedom this whole system has? So this whole system can move in three directions, transitional, x, y, z. Okay, so we have three transitional degree of freedoms. Now it can rotate whole system in the, with x-axis as the its axis. Okay, so it can rotate like this. Now it also can rotate with a y as its axis, rotational axis. Then it can rotate like this or like this along the y. Okay, and it also can rotate, or we will call it spin on the z axis, just like this. Whole system can spin over this. Okay, so means but this spin on the z axis required a lot amount of energy, which is possible only at the very high temperature, means more than 1000 degrees Celsius. That's why we consider that this diatomic molecule can have only two rotational degree of freedom, that is this and this. Okay, so three transitional and two rotational. Okay, and there is one more thing. At high temperature, not very high but a normal high temperature, we can observe that these particles can oscillate also. Means just like take this, these are there, so it will act like a spring between them, this force, so they can vibrate. So we already discussed in the solid state physics that there will be one mode possible for this uh, diatomic vibration, and this one mode will give you two energy terms. Means this one mode will have one kinetic energy term and one potential energy term. Okay, so this one vibrational mode will give you 2 degree of freedoms. Okay, because each square term of energy will give you 1 degree of freedom. Okay, so you just have to count the square terms. So here in one mode you will get two, which is one from kinetic energy, one from potential energy. So 2 degree of freedom with one mode. So only one vibration mode is possible with 2 degree of freedom. 2 degree of freedom at vibrational, two at rotational, and three at transitional for a normal high temperature for the diatomic. Okay, so we will discuss them more further in detail in the next section. Just here you just get a better understanding how we are gonna see these things. So now we can talk about the triatomic. If we talk about the triatomic, then we see that if they can be linear or they can be non-linear like this. Okay, so both cases are possible. So here if these are linear, so just put these three in this case, 1 2 and one more here, 3. Then again rotational will be 1 2, and spin is not possible, so 2 rotational and 3 transitional, and vibrational will be this one mode from this, one mode from this, and each mode will 2 degree freedom, so 2 to 4, 4 vibrational, 4 degree of freedom at the vibration mode. Okay, so 4, 5, 6, 7, 8, 9, so 9 will be possible for the linear, and but in the non-linear case we see the rotational motion. This is possible, this is possible. Now this along the z-axis is also possible because this can rotate like this. So 3 rotational, 3 transitional, and at very high temperature means we will consider the vibrational mode only at the high temperature. Okay, if it is written in the question explicitly that temperature is high, only then you will consider the vibration mode. Okay, so 1, 2, 3 vibration mode will be possible. So 3 will give you 6 square terms. So 6 degree of freedom with vibration, 3 with rotation 9, and 3 with transitional 12. So here you will get 12 terms. So just like this, if you want to calculate for the vibration, so just count how many these pairs are forming, and each pair will give you 2 square terms. So that's how you can calculate. So this was just a brief idea how to check the degree of freedoms and the rotational vibration and all. We will just go in detail in the fewer minutes later. So what is degree of freedom? This is refers to number of independent squared energy terms in total energy expression of a molecule. Okay, so let me give an example for you. Just like this is a 3D space, so this particle, so if a single particle is moving, so it will have a 3 energy terms independent of each other, which are 1 upon 2 m vx square plus 1 upon 2 m vy square plus 1 upon 2 m vz square, means kinetic energy in 3 directions. So 3 square terms we are getting, so that's why we have 3 degree of freedoms here for a single particle. And that's how when vibration mode conduct, then one kinetic energy, one potential energy, so 2 in one mode. And in the rotation motion we are taking that one this way, one this way, so that's how we are calculating the degree of freedom. So this is nothing but total energy, total square terms in the total energy expression of a molecule. So here's one more thing, that is equipartition theorem. So the proof is also available, but we will not discuss proof now because it will come when we study the statistical mechanics in the thermodynamics. Okay, then we will study that how the equipartition theorem is proved, because now you will be unable to understand the thing because it is a little complex and it includes statics. So we'll study it later. Just here we will take the expression what equipartition theorem says. So for a system of n molecules, each with f degree of freedom, a system which have n molecules and each having the f degree of freedom, then total internal energy or thermal energy will be given by n dot f 1 by 2 kt. N is number of molecules, f is degree of freedom, and this. So if there is only 1 degree of freedom and there is only one molecule, so this will give you half kt only. So that is called the equipartition theorem, means in any 1 degree of freedom a single molecule will have half kt of energy. Okay, so this is the general expression for the equipartition theorem. So just remember this formula, it will be helpful. Now we will see some applications of the equipartition theorem. So as I told you, just now we will calculate the energy of different systems with the use of equipartition theorem. So mass spring system, if this is a rigid wall and this spring is attached with this m mass, now this can oscillate in only one direction. So 1 degree of freedom is possible. 1 degree of okay, it's possible, but as I told you, it is vibrating, so it will have 2 energy terms, that is kinetic energy and potential energy. Just like this, 1 by 2 m x dot square, x dot is nothing but velocity square, plus half kx square. K is spring constant here, not the Boltzmann constant. So this will be the energy, so we'll have 2 square terms, so 2 half kt will add it, and this will give you the total energy of the system. Okay, so just remember what we are discussing. For the one monoatomic gas molecules, we already discussed half mv x square, vy square, vz square. That will give you p square by 2m, py square by 2m, pz square by 2m. So 3 square terms. So that's why 3 by 2 kt. and for 1 mole that will give you 3 by 2 RT, and I already told you degree of freedom 3 because 3 square terms. Cv will be dq by dt, constant volume, u will be equal to q, so it will give you 3 by 2 r. Cp will be this, and Cp by Cv will be this. So just remember, this adiabatic index is maximum for the monoatomic gases only, means it will decrease with the atomicity, but this will be the maximum value. Okay, this is possible maximum value for the adiabatic index. Now let's discuss for the diatomic gas molecules. So I already told you this, the transition will be 3, rotation will be 2, and vibration is 2 only at the high temperature. Means here I told you na, this diatomic molecule will rotate 1, 2, and 3 transitional 5, and when temperature is high, then 2 from the vibration, then 7. Otherwise it will be normal, 5 degree of freedom will be possible. So if we talk about rotation, then you will be considering that why we are not considering this spin. So here rotation energy is given by half L square by I. Here I is moment of inertia, L is angular momentum. So moment of inertia is nothing but mr square. So for the spin case, this I2 will be very less, so this term will be very large. So to activate this motion, this spin motion, we need very high amount of energy, which is not possible given at the low temperature. It will require a very high temperature. That's why we will consider this mode only when the temperature is very high. Otherwise 2 rotational are possible only. So we'll consider these 2 rotation of freedom. That's why I written Fr equal to 2. And vibration is also considered at high temperature. Otherwise we will have only 3 to 5 degree of freedom. So vibrational motion of diatomic gas molecule will be kinetic energy and potential energy term. 1 mode is possible, so this will give you 2 square terms and 2 vibration. That's how we written Fv equal to 2. This is nothing but this is came from here R1 R2. So R2 minus R1 will give you this. So dot will give you the speed, so kinetic energy dot, and if normal, that is potential energy. So one vibrational pair contributes 2 squared energy terms. That's why 2 degree of freedom. Vibrational degree of freedom are excited at higher temperature only. So if it is written in the question that temperature is high, only then consider the vibrational mode, otherwise not. So total degree of freedom for diatomic molecule will be transitional, rotational, and vibrational 3, 2, 2. Okay, that will give you 7 and 7 by 2 kT. So for the 1 mole, it will give you 7 by 2 RT. Now at ordinary temperature, Fv will not be considered, and diatomic molecule will have 5 by 2, 5 degree of freedom, then 5 by 2 kT, 5 by 2 RT, Cv will be 5 by 2 R, Cp will be Cv plus R, that will save us 7 by 2 R, and gamma will be 1.4. So examples are hydrogen, chlorine, and oxygen, etc. So we get the gamma value decreased from the monatomic gas. If we compare with the monatomic gas, so it is decreased. So according to the experimental data, we are going right, and what we are discussing is right. Okay, so now let's check for the triatomic linear gas molecules. For linear case, this is like this. Okay, so now this mode is possible rotation, and this mode is possible. Only 2 rotation are possible and 3 transition are possible. And if we talk about vibration, then 1, 2 mode will give you 4 square terms, so 4 degree of freedom with the vibration. Transition 3 Fr2, and this will only at the high temperature. So triatomic non-linear will give you, so this is for the linear, so you can calculate from here the total energy and the heat capacity and all, just the same we did. Okay, only main thing is to calculate the degree of freedom. I have given you these things. Now for the triatomic non-linear, if the case is non-linear, so I already told you this is the non-linear case. So one is this rotation, one is this rotation, and one is this rotation. So all 3 axis rotation are possible because it is non-linear. So that's why we will get 3 rotation terms, 3 transitional terms, and 1 mode, 2 mode, 3 mode will give you 6 squared energy terms. So you will get total 12 degree of freedoms at higher temperature for the non-linear case. 3, 3, 6, 6, 12. So energy will be 3 kT means this is 6 when temperature is normal, and we will not consider vibration mode. That will give you this energy. Ordinary temperature, this will be the energy. And but at high temperature we will consider all the 12 degree of freedoms. That will give you 6 kT. Okay, so I hope you get the idea. Now rigid versus non-rigid bond. If it is written in the question that system is rigid or non-rigid, what's that mean? So rigid means the distance between two particles won't change. So that particle or the system won't have the vibrational mode, because the distance can't change, then they can't vibrate. But it is given that non-rigid, then vibration mode will be considered. So when rigid, vibrational degree of freedom will not be excited, ignore FV, and vice versa, means it is given non-rigid, then consider the vibration mode. Now as general relation, we can find heat capacity and degree of freedom. For a system with F degree of freedom, we know that how much energy is this. I already give you this formula in the equipartition theorem. So for one molecule, N will be 1, F will be degree of freedom half kT. So per mole, that will give you F by 2 RT. This is NaKb will give you R. Then Cv will be dq by dt, that is du by dt, that will give you F by 2 R. Cp will be Cv plus R, that will give you 1 plus F by 2 R. And gamma is adiabatic index, that will give you the ratio of the Cp by Cv, and it will be this. So this is the general formula, just you can calculate directly from this, the gamma value or the Cp value or Cv value you can calculate directly, just knowing the degree of freedom. Now let's discuss two questions. These are questions asked in the previous JEST exam and NET exam. So there are more questions. I will provide them on the practice set series. Just solve them there. Here I taken this example just for the get you idea that what type of questions can be asked. A specific heat per molecule of a gas of diatomic molecule at high temperature is. So we need to give the diatomic molecules a specific heat. So at high temperature, so vibration mode is also considered. 3 transitional, 2 rotational, 2 vibrational for the diatomic. So 5 to 7, 7 by 2 kV for one molecule. So they will give you 3.5 kV. This will be the answer. A system of n non-interacting classical point particles is constrained to move on the 2D surface at a sphere. Internal energy of the system is. So this is a spherical system, and inside the particles are only constrained to move the 2D motion, to have the 2D motion. So each particle have how much degree of freedom? Only 2. So each particle will have energy 2 into half by kT. This will kT. So each particle have this. So n particle will have n kT. So this is the answer. So I will give you more questions on the practice series. Okay, solve them there. Here we will end this discussion here. Okay, I will bring more videos on the thermal physics. There are gonna be 40 lectures, and we will complete the all thermodynamics. So just keep on doing this and the practice. Okay, and be consistent. Thank you.